Good afternoon, everyone. I am actually so glad to be here today. This is my first time at VCF, never been before. I actually plan on coming out here in 2020, but there was a small little problem with 2020. Happened to be the same weekend as my wedding anniversary. So I decided to try to negotiate with that, and I don't like going out for Valentine's Day. So I said, hey, if I go out for Valentine's Day, can I come to the VCF in April instead? It was a tough negotiation. I was able to make the deal. So we went out and had a great time on Valentine's Day. Then the pandemic hit, and I spent most of April watching reruns of Stargate SG-1 instead. So, but I'm here today. It's 2022. Our anniversary is now on a Monday, so no worries there. So I'm sure that many of you in this audience are familiar with this computer. This is the Commodore 128. This is the computer I spent a lot of time learning how to program when I was a kid. Now, I apologize if I just called you old out there because I said I was a kid when I had this. But this is the Vintage Computer Festival, and like it or not, none of us are getting any younger. I actually bought this exact one from a friend, Eric Chomko, who is here today. Everybody give a shout out to Eric Chomko. He'll probably try to sell you something this weekend. So. He loves to collect old computer equipment. His wife actually keeps trying to get me to buy stuff from him anytime I come to visit. So I took him up on the offer one time and bought this. I have since acquired a Commodore 128D. I got this from my wife's father, Larry Sawyer. This was sitting around collecting dust, so I figured I'd provide a nice home for it. This is how I have it set up at home right now. This desk is usually not this clean. It tends to be a magnet for clutter. So. But it's been really fun playing with the Commodore computers again, and it sort of got me thinking, you know, how much would it take to write an emulator for the 64? Now, I don't want to do anything completely comprehensive or anything like that. I don't have time for that. But how about enough just to get up to where you can actually type in a basic program, everybody's favorite, Hello World, and of course, go to 10, because you have to say go to 10. So that's what we're going to talk about today, is basically how to get from scratch up to getting to Hello World. Quick disclaimer, I am not an expert on emulation. I just happen to have written an emulator. I'm also not an expert on the Commodore stuff. I just happen to own one. So everything I go over today, I hope is correct, but there's always a chance something's going to be wrong. And of course, we're going to concentrate on getting things to work, not necessarily to do it in the best or most efficient way. So the agenda for today, we're going to spend the first 15 minutes talking about memory. Then we're going to spend the next 15 doing an actual CPU implementation. We're going to actually be doing a lot of code in that section there. The next 15 minutes is going to be from there to get to Hello World, and then we'll finish with a Q&A session at the end. So let's first talk about memory. On a CPU like this, we have an 8-line data bus. We also have a 16-line address bus. And with those 16 lines, you can access up to 2 to the 16 different values in the address space, which is 65,536, also known as 64K. So when you're going to write an emulator for memory, you may be tempted just to have one huge array that is 64K in length. So 64K array of 8-bit values. Now the problem with this, it's a little bit too simplistic. It doesn't actually really model the way that the CPU actually interacts with the buses, okay? So while most of the time the CPU uses the buses to talk to memory, whether that be RAM chips or ROM chips, it can actually use it to talk and communicate with other chips or devices on the machine as well, whether it be the sound chip, whether it be the video chip, and can actually talk on the bus to be able to manipulate the lines on the back of the computer for the user port. So what you could actually do is take one of those lines on the user port, hook it up to a relay, hook up that relay to your desk lamp, and then tweak a value in memory to turn your lamp on and off. That's pretty great. Now, I would recommend doing that because it's really easy to fry your computer if you do something wrong this way, and they don't make Commodores anymore. So if you want to have that kind of fun, buy an Arduino. They're only $6 if you screw them up. You have to buy a new one. At least it was before the chip shortage. I'm not sure how much they cost now. It might be $60 now. I'm not sure. So we're talking about the Commodore 64. It actually came with 64K of RAM. As we're talking about before, we only have 64K of addressable space. So where does everything else go, such as like the ROM chips? So of course, a common technique used in the day is that we map these ROM chips into the address space as needed. So here's an example here on the Commodore 64. We actually have the basic chip mapped in at A1000. We have the character generator ROM mapped in at D1000. And then we actually have the kernel mapped in at E1000. And the great thing about this is that, let's say you're writing something that's in pure machine language and you don't need the basic ROM in, you can just sort of map that out and you get access to more RAM for your program. So on the Commodore 64, there's actually 5 latches that control the memory configuration. 2 of these are controlled depending on what's plugged into the expansion port. The other 3 can be manipulated by the programmer at runtime. So that gives you a full 32 different combinations here. Some of these are redundant, but if you actually follow all these here, you'll actually get a correct implementation of memory. We actually had to do a switch out of laptops real quick, so I had some speaker notes. I think this is on c64wiki.com. So it is somewhere on the web. So you have to actually just follow this table, and you're actually pretty good to go when it comes to setting up your memory. Another thing, so what we sort of talked about before is that having a huge array to represent memory is just not good enough. What we really want is actually have an array of mappings to actual memory locations. Okay? So that way what we can do is change at runtime what each memory location points to. Okay? So this is an example here what we had before. We're in the low space of memory. We actually have RAM here. And then up in the A1000s, what we're doing here is we want to map A1000 to point to the memory address 0 in the actual ROM itself. And A1 goes to 1, A1002 goes to 2. Okay? So we want to be able to dynamically change the mapping at runtime. Another thing we have to worry about is, so what happens if you actually write to a memory location where ROM is mapped in? Now, I didn't know. I thought it's read-only memory. So if you try to write to it, nothing's going to happen. Well, actually, what really happens is that if you try to write to it, it actually writes to the RAM underneath that. Okay? So we actually have to worry about actually having asymmetric access as well. So for any given memory address, what you read from could be totally different than what you write to. Okay? And for the Commodore, this is probably the only place you're going to have to run into that. But I actually did some other work as well with like a Pac-Man emulator. And there's a lot more of this going on. So it's important to realize that this is something that can actually happen. And I only discovered this when I was actually looking at the Commodore 128 startup sequence. What I was finding was some part of the code was actually copying memory from itself to itself. So it'd be like load 4000, store 4000, load 4001, store 4001. I was like, why is it doing that? That makes no sense. Well, then I learned about this. I was like, oh. So I suspect what it was doing was basically copying the data from ROM into the RAM so that when the ROM gets spanked out, it's still available in the RAM as well at the same address space. Okay, so we've talked about all the different kind of things we might have to deal with. So let's go ahead and actually start working on our actual memory structure. Now I'm going to be writing these code examples in Go because I actually wrote my emulator in Go. Has anybody used Go? Do you like it?
Yeah.
Okay. A little bit of a pause, so maybe not, maybe not. So hopefully, if you have some programming experience, this should actually be pretty readable. It's kind of a C-style kind of language. If you're not a programmer, hopefully my narrative will be so exciting, you'll want to stay anyway. So the first thing we want to do is actually just provide 2 functions that will be the interface to our memory. We're going to have one for reading from memory. We just provide an address and returns an 8-bit value. We're going to have one for writing. We're going to give an address and give it an 8-bit value. And we're going to do this because as long as we keep these 2 functions the same, our underlying implementation can change. So we already talked about that we don't actually want to have one huge array of 8-bit values. Instead, we want some kind of mapping. So a good way to do this is actually to have 2 separate arrays, one for reading and one for writing. And instead of actually having 8-bit values, we'll actually have functions that actually do the reading and the writing. And then we can sort of change these as needed at runtime. And if you do it as a function, it gives you the most flexibility to do whatever you want. So that way, if somebody writes to a memory location, you can actually do the remapping of memory if you want. You can call any kind of function you want. It doesn't matter. So I actually went through 3 different implementations of memory before I landed on this one. The first one, I did things page-based, because that made sense for a Commodore, but didn't for the Pac-Man. I did one where everything was just pointers instead. But then I realized actually this actually provided the most flexibility. So I'll save you the trouble now. This is probably worth doing it this way. Okay, so once you have that, then it's just easy enough to provide some functions that sort of assist in doing these mappings. So say we actually do have a chunk of memory in an array of 8-bit values. We can provide 2 functions, one for mapping RAM, one for mapping ROM. When we call map RAM, we're actually going to do the writers and the readers at the same time. When we call map ROM, we'll actually only update the readers. Now, if we want to do a single value, and this is actually useful for basically certain registers on other chips, where we want to map in one value to a specific memory location, we can provide a map read-write, map read-only, map write-only, and then provided a pointer to an 8-bit value. And then when we want full control, we can provide a map reader and a map writer and actually give it those functions that it really wants. So we'll go ahead and actually do the implementation for one of these. We're going to go ahead and do the map ROM function. This function is going to take 2 arguments. One is going to be the base address of where we're going to map this into. The other one is going to actually be the data array that we want to map in. Now, let's say this data array is 4K of values, okay? You may think we actually have to instantiate 4K worth of functions in this kind of mapping, but we actually only have to write one, okay? And we're going to use basically a closure to do this. So we're going to write one function here. It's going to take an address, return the value, and it's as simple as basically referencing into this array here and taking the address minus the base, okay? That's all we have to do. We only have to write one function. Now, it's sort of like go into more detail what's happening here. Here's our original mapping that we had before. We basically have a ROM mapped in at 8,000. So what want to happen is that if you do something like 8002, you actually reference index 2 into this array. So let's say we take map ROM, pass in 8,000 as the argument. Now with this function here, if you happen to pass in 8002 to read from that address, what will actually happen here is be 8002 minus 8000, which will give you the correct value of 2. Okay? That's how you do your mapping. And then we now just need to copy this into the address space this way, just by looping over it. Okay, so we're going back to original example here. We're actually going to try to do the original bank implementation. We actually have basic the other ROMs mapped in. So we'll first do our mapping here by calling map RAM. We'll provide a RAM variable that has the 64K chunk of memory and say map at 0,000. So it's going to do the read and write mappings for both of those. Now we call map ROM to put the basic on top. So we pass in an array with all the basic information at 8,000. They'll actually update all the readers for that location, but actually won't adjust the writers. So that way, actually try to write that location, it'll actually hit the RAM underneath. And then we do the same thing for the charge in ROM and also the kernel. And that's basically how you sort of do your mappings. And anytime you want to readjust memory, you just recall the mappings and you're good to go. Okay, so now that we actually have talked about memory and went through a quick implementation of that, we're now going to talk about the heart of every computer, which is the CPU. This is a photo from inside my 128. I probably should have cleaned it up a little bit before taking this picture. It looks pretty bad there. But the 120 is actually the 8502, it's a variant of that. So we're going to be talking about that. Of course, if you're a Commodore fan, the 6502 is your second favorite chip, because you know the first one's the SID chip, right? So if you want to be able to understand the machine you're going to emulate, you need to be able to speak in the language of the machine. And I learned how to speak 6502 by reading this book, Machine Language for the Commodore 64, 128, and Other Commodore Computers by Jim Butterfield. I tell you, this was actually a really good book. I highly recommend it. If you want to learn 6502, this is the book you should get. I actually still have this book. So it has survived till today. So now if you don't have this book, there's good news. There's actually a PDF of this available up on the Internet Archive for download. The Internet Archive is a great resource. And they actually have a lot of back issues of Compute's Gazette as well. So if you're interested in those, I know what you'll be doing later tonight. So, okay, so here's an example of an instruction that we would like to try to emulate. Okay, so this is the instruction to store the contents of the X register to memory location 381. In memory, it looks like this. So each instruction starts off with an 8-bit opcode. With the 6502, it's always 8-bit. The opcode for this is actually 8E. Then each instruction can be anywhere from 1 to 2 to 3 bytes in length. This one's actually 3 bytes in length. And what follows the opcode here is actually the address, which is 8103. It's actually backwards in memory because this is a little endian architecture. That's the way that works. If it was the correct way, it'd actually be the big endian. But actually, the cool machines do it the little endian way. So, and the example I picked is actually the example is actually on the front cover of this book. As you can see, the 0 character there is actually saying the instruction, and then the 1 character is saying how it looks in memory. Okay, now how cute is that? So, whoever came up with that, that's great. So now we'll start working on our CPU implementation. We're going to start with the structure to begin with. The first thing the CPU needs is its view into memory. So we're going to give a pointer to our memory object we created earlier. We didn't have to work on our registers. The first thing we're going to need is the program counter. This is a 16-bit register that will tell the CPU the memory address of the next instruction located in memory. We then have our A, X, and Y registers. These are 8-bit registers. A is the accumulator, where all the fun math happens. X and Y are used for indexing. You can also use all 3 for anything you want as well. We also have a stack pointer. We also have the status register. Now, the status register contains various flags. These flags contain the results of the previous operation, or they can be set and cleared to control the operation of the CPU itself. So as we write our implementation, we're going to be working a lot with the status register, but we'll actually be working with the individual flags. So we actually want to be working with the individual bits on a regular basis. Okay? So there's a couple ways you can actually go around doing this. You can actually just have, these are actually the flags. So I don't have my notes ready. I'm sorry. But these are actually the flags that we're talking about here. I'm not going to go into detail about these flags. But the one way you can do is actually have some constants here to basically represent your flags and do all your standard bit twiddling tricks to turn the flags on and off as needed. What you could also do is just provide some convenience functions. For example, let's provide a function called C that return the results of the C flag as a Boolean, as necessary. Or you could flip it around. Instead of storing the status register in the struct, you can actually store the individual flags as Booleans. And then what we could do is actually have a status register function that will return all of them or together in the times you actually need to work with the full status register. So there's a couple different ways you can do this. I picked the first way. For the remainder of today, we're going to do this way because it's a little bit easier to read the code on the screen. Okay, our basic run loop is actually quite simple. It's going to start off simple. It's going to get more complicated as we go along. But at the beginning, it actually does start out pretty simple. The main job of the CPU is to fetch the next instruction from memory and then to execute it. So we'll put our example instruction back on the screen here. The first thing we have to do is write our fetch function. In this case, it's going to get the next 8-bit value in memory according to what the program counter contains. One thing to note about the 8502 is that the program counter is actually 1 byte behind where the next instruction is. So when it's time to actually fetch the next value, you actually have to increment the program counter first. Then I'll put it in the correct location. And then you want to return the contents of memory found at where the program counter is. Now this is how it works on the 6502. Note with something like the Z80, it's the other way around. You actually want to get the value first and then increment the program counter. So something simple like that can be different depending on which processor you're working with. Okay, now we're ready to write our first instruction. So we're going to start off with a logical AND. The great thing about writing an emulator is that the programming language of choice that you're using most likely has a lot of these operations already built in. So if we actually want to do a logical AND between two values, v1 and v2, and then store the result of that in a variable called r, this is how we write it. Now, with the 6502, you can't actually basically have two operands that are arbitrary. The first one always actually has to be the accumulator. And then the final result also has to go back into the accumulator. So our code now looks like this: cpu.a equals cpu.a and v2. Now, where do we get v2 from? So we're first going to talk about the immediate form of AND. And what this means is that the value of v2 is actually going to be the value that's found in memory immediately following the opcode. So for this instruction and immediate 42, in memory looks like this. It's 29 for the opcode, and then 42 for the value. So to get the value of v2 is really easy. We just call the fetch function that we just wrote. Now we actually have to set the status flags according to the last operation. With AND, there's two that we're concerned with. One is the Z flag. This is the 0 flag. It gets set if the result of the previous operation was a 0. And then we have to work with the N flag, which is the negative flag, or also called the sign flag. This is set if the result of the last operation had its 7th bit set. This is how we write it. So this is the full implementation for immediate AND. It's only 4 lines of code. But there's more than one AND. There's actually 8 different ANDs. Okay? And these basically only differ by how we actually get that value of v2. And these are called the addressing modes. So these are the actual 8 addressing modes supported by the AND instruction. So we already talked about immediate. Then we have the ones where we're actually going to read the value from memory instead. So in the second one here, that's actually going to read the contents of memory location 12, and that's going to be the value of v2. Okay, I'm calling it absolute 8 here. This will also be called 0 page in the documentation. We'll have ones where it's a 16-bit value for the address. This way you can actually, these instructions can be shorter if you can actually stuff them lower in memory. We got values indexed by X, indexed by Y. We also have some indirects as well. So let's go. So this is actually the table I use while implementing my version. So you go to 6502.org. This lists every instruction on the 6502 in a nice tabular format, has all the addressing modes supported by each instruction, and then it tells you which flags are affected by it. I do recall this is written by John Pickens and later updated by Bruce Clark and Ed Spittles, if I'm correct. So this is a very handy reference to get. So let's go back to our original implementation. Let's go ahead and write the instruction for when we want to get the value from memory location 42 instead. Well, that basically only changes by changing how we get v2. So now when we call our fetch, that fetch is actually going to be the address. And then we actually call a read to get the value from memory. That's what v2 is. So for all these, that's all we need to change. So we don't actually have to do 8 separate implementations of AND. We actually only need to do one. And then what we'll do instead is actually we'll pass in a variable called load. That's actually a function. And then that function, when we call it, will actually return the 8-bit value that we need. So this way, the implementation of AND doesn't have to worry about where it gets this value from. Okay? It could be absolute, it could be indirect, it could be indexed, it doesn't matter. Then what we can do is actually implement all of our addressing modes by passing in different functions for load. Let's go ahead and do that. So for load immediate, this is how the function would look. It simply returns an 8-bit value. We just call fetch. That's all it is. Now let's say we want to read from memory using an 8-bit address. We already did this already. Same kind of thing. We call fetch. That's what we use to read from memory. So now let's do absolute 8 indexed by X. Basically the same thing here. The only difference is after we fetch, we're actually going to increment that value by the contents of the X register and use that as the address to read from memory. So we write one of these functions for each of our addressing modes. We're doing a lot of loads here, but we actually want some store equivalences too. And then you're ready to start building your opcode table. So we're going to have an opcode table here. Basically going to have all of our opcodes that are supported by the processor, and then the functions for each one that we should execute when we see those opcodes. So we're going to do our first one here. This is our immediate AND. It has opcode 29. So when that gets seen in memory, we're going to call this function here. It actually calls our AND implementation, but with the load immediate addressing mode function. So now we'll do the next one, opcode 25. Same thing. We call our same AND implementation again, and this time we'll pass in the load absolute 8 addressing mode function. And we just basically do this over and over and over again for all the different addressing modes, and we're good to go. Now we just have to implement all the other instructions. So for the 6502, there's a total of 151 opcodes. As you can see before, we don't actually have to write 151 functions, but we do have to write 37 of those. Some will be harder than the one we wrote, but some actually will be easier. Actually, 11 of them are so trivial, you can write them in a single line of code. Now, my full implementation was 599 lines of code. So if you think writing a 6502 CPU emulation is a huge undertaking, it really isn't. Okay? Now, I did write 2,800 lines of test code. Now, part of that is I didn't write them efficiently. I did a lot of cut and pasting. Don't tell anybody that. The other thing also is that you really, really want to do as much upfront testing as you can now, because any bugs you find now are easier to solve than later on when you're running the kernel through your emulator, and then something doesn't work there, that's going to be a lot more difficult to find out. So do the best you can up front, do as much testing as possible. Okay, now we're ready to write our CPU function called next. And what next will do is basically just execute the next instruction. Okay? We've already done this already. So we're going to call fetch, that returns the opcode. We're then going to look up that opcode in our table, and that's going to return the instruction function that we want to execute. Then we call the instruction, and we're good to go. It also returns a value called OK, which is a Boolean, letting us know if that opcode was found in the table or not. And if it wasn't found, well, then it's an illegal instruction. There's nothing we're going to do at this point. Now, on a real CPU, if you give it an illegal instruction, it's going to try to do something. But we're not concerned about that right now. Okay? If we're trying to run something that's using illegal instructions, we're probably in over our head at this point. So a better option here would actually be to log this out, put some kind of warning, so that when you're actually testing this kind of stuff, if you have a condition you're not expecting, at least you're notified of it. So I highly recommend that. Now we're ready to go back and modify our run loop. And it actually is now time to create our machine structure. This is what we're going to use to collect all of our various components of the machine we're emulating. So far we actually have memory. Actually also have our CPU. Now we're going to write our run loop, which is pretty simple. Basically, it's going to call CPU next and do that in an infinite loop. So that's how we get started. Once you've done all the instructions, it's now time to do some minimal tooling. At a minimum, we need a memory inspector. We want to be able to view the contents of memory at runtime to make sure the computer is doing what we expect. And of course, at times, it's not going to do something that we expect. And in that case, we may want to trace the execution of the CPU to sort of get a clue of what's going on. In order to write that, we're going to need to have a disassembler. And as bonus points, you can take all these tools and bundle them up into a runtime monitor. You don't necessarily have to do that. I find writing this tooling to be fun, so I spent way too much time on the monitor. I shouldn't have, but you know, it's a fun project, right? Okay, so now, after we've done that, we're basically ready to sort of power on this emulator to see if it does anything yet. There's only a couple more details we have to take care of. We actually do need to get some ROMs and load this into memory. We're doing the Commodore 64, and we talked about earlier, there's actually 3 ROMs we're concerned about. The best way to get these ROMs is literally just go download the Vice emulator, install it, go look through the file system until you find the ROMs, and then copy them over into your emulator. We then have to handle the CPU reset. When the computer is first turned on, the reset line is asserted, and at that point, there's the reset vector located at FFFC that contains the address of where the program should start on a restart. Now, we don't have video up yet, but what we can do at this point is actually just look at video memory. And that's located at 400. So what we're going to basically do is look through there and see if we actually get the classic Commodore startup banner. So let's turn it on and see what happens. And if you do it the first time, you're going to get this. Okay? This is a whole lot of nothing. Well, actually, it's a little bit of something, because actually these are all 20s, and 20 is the space character. If it was actually a whole lot of nothing, it actually would have been a whole bunch of zeros. So, at this point, probably it did try to initialize. It cleared the screen, but it didn't make it any further than that. So why did this happen? I don't know. So this is where you actually go through and actually say, okay, let's try to trace the execution and see what happened. So when we do that, we start looking, and you can see that the CPU is caught in this infinite loop here. So what it's trying to do is actually read from memory location D012, and it's branching back on itself until that value is 0. So for some reason, this is not 0, and it's waiting for that to happen, and it's never going to happen. Why is this memory value important? I don't know. I am not a Commodore expert. But who is an expert is Sheldon Lehman. He wrote this book called Mapping the Commodore 64. And in this book, it actually details every single memory address and tells you what it's used for. I don't have a copy of this book, but once again, you can get a PDF of this off the Internet Archive. So if we download the PDF and open up to the page that talks about D012, what it'll tell you is that this is actually a register that contains which line on the video screen is currently being scanned. So what I suspect is happening here is that it's actually waiting for the video chip to initialize, and it's waiting for that for the scan line to get up to the top for the first time. That's just my suspicion. I'm not sure if that's the case or not. So what do we do here? We haven't actually done anything with video yet. We don't necessarily care about this. So basically what you do here is you basically just give it what it wants. So at the beginning of our for loop, we're always going to write 0 out to D012. Okay? Is this correct? Absolutely not. Will this work? I have no clue. But the fun of writing an emulator is trying these things out to see what happens. Okay? Our main concern right now is just trying to make more progress. Right now we're stuck. It's waiting for 0. We'll give it a 0. Now, sometime later, you may actually want to fix this. So it's important to take notes and remember that you actually put this in. You don't want to come back 6 months later and totally forgot that you had done this. So when we do that, let's fire it up again. Now when we look at memory, we actually do get the classic startup Commodore 64 banner. The problem is, with my implementation, when it came up for the first time, it actually said there are 0 basic bytes free. Well, there's definitely more than 0. Why is it saying 0? I don't know. Maybe it's trying to take the total value minus the used, and that's the free. So maybe there's a bug with my subtraction. So I went looking through the subtraction code. I couldn't find anything wrong with it. I suspected maybe a couple other instructions as well. Didn't find anything there. So I did a lot of upfront testing, but it looks like my testing wasn't comprehensive enough because we still have a bug. So what do you do in this case? Well, you go find somebody else who wrote tests. So I found this repository here. This is written by Klaus Dorman. This is actually a test written in 6502 assembly, meant to be run on an actual processor. And the way this test works is that you run it, and eventually the CPU will get trapped at a certain memory location. At one location, it means the test was successful, everything is correct. If it gets trapped elsewhere, that means you have a problem. And where it gets trapped will give you an indication of what the problem is. So I ran this through, and of course, there was a problem with subtraction. So I actually looked through that a little bit more in detail, and I realized that I actually set one of the flags wrong. So I fixed that, and now we get the correct startup banner. Everything's looking great. So now it's time to move on to video. I was actually hoping to spend quite a bit of time talking about video, but with only an hour, there wasn't actually enough time. So for this last bit of stuff we're going to be talking about today, we're going to go through this pretty quick. So I implemented it using SDL2. That's a simple direct media layer library. And for video, what we want to basically do is have a window that pops up with a display. And we want to render a frame 60 times every second. In order to render that frame, there's a couple places we want to get information from. One being the background color, that's stored at D021. We need the border color, that's stored at D020. And then we actually need the text. We've already looked at that before with the monitor. That text is found starting at memory location 400. And then the color RAM is actually stored at D800. So, and the basic strategy here is you actually want to have two images. So the first we want to do is actually generate a tile sheet over here. So we're actually going to look at the character generator ROM that contains all the bitmaps for the characters we want to display on the screen. So we have to do this once. On startup, we just create a tile sheet here of all the possible characters that we have. And then we'll have another image, which will be our render target. So each time that we need to render a frame, just blank it out with a background color. Draw 4 rectangles. That will be the border. Then for each column and row in the text display, you basically just want to find it in here and then copy it over to there. That's all to do video to start, at least for text video. So, and actually a lot of things on the Commodore was text video anyway. You play some of your favorite games, it was text mode. It didn't look like text mode, but it actually really was. So once we do that, we get that up and running, and we actually have a beautiful start screen at this point. But what we don't have yet is a blinking cursor, because we actually haven't dealt with interrupts yet. Okay? So 60 times a second, the CPU is interrupted to perform certain administrative tasks, such as blinking the cursor, and scanning the keyboard and stuff like that. This was a nice animation of a blinking cursor, but not with a PDF. I apologize for that. So 60 times a second, there's a tug on the IRQ line. When that happens, the CPU finishes execution of the current instruction, then it starts the interrupt sequence. It does that by pushing the contents of the program counter and the status register to the stack, then sets the interrupt disable flag so it doesn't get interrupted while doing the interrupt, and then transfers control to the interrupt service routine. Memory location for that is actually stored at FFFE, that's the interrupt request vector, and then that actually runs until it hits an RTI instruction, return from interrupt. And then the sequence goes in backwards. The return execution to the original program. So now we have that. Now it's time to do the keyboard. Now what we can do at this point is that we can actually cheat. Okay? We don't actually have to do a full keyboard implementation. Now we can sort of take advantage of the fact that we know how we can actually do the work for the computer ourselves. So we know that there's actually a ring buffer at memory location 277. That's a 10-byte ring buffer that contains the keys that have been pressed. Indexed into that ring buffer is stored at C6. And what we can do here is we'll actually pull SDL for keyboard events. When we get an event that one of our keys have been pressed, we take the Mac key or the Windows key or like that, convert it to an appropriate Commodore key, then we can just stuff it directly into the buffer itself. Okay? This is cheating, but this is the easy way to start. So when in doubt, you can try the cheat first to see if it works. And if it doesn't, that's great. You can actually just go ahead and do a real implementation. But right now, we can try the cheat to see if that works. The other thing you have to be concerned about is the stop key is handled separately. That's actually stored at memory location 9.1. I basically mapped the run stop key to be basically if you press Control-C. Okay? Once you do that, run that, you get an emulator up and running. Everything's looking great. You can actually finally type in your Hello World program. This basic program is a little bit more complicated. Actually, my basic is so rusty, I actually had to look up how to write this. So, this is basically everything you need to know to write a basic emulator for the 64. I'll let you decide if that was a pun, if it was a basic emulator. So once you've done that, you got a working 6502 implementation. You can continue to work on the 64. You can actually do some other Commodore stuff if you want to. You could do a 128. You could do a VIC-20. Why not? Or you could actually do some other things as well. Some of my favorites have 6502s, such as the Atari 2600, Apple IIe, Nintendo Entertainment System. Now, I haven't tried any of these. I don't know how difficult they are. But once you have something up and running, you can actually use that work for something else. Okay, so that's basically it for today on how to write your basic emulator. Now, in the event I've inspired anybody out here to write their own emulator or to give it a try, I do have a couple of tips for you. One thing is, at the very beginning, you need to collect as much documentation up front as possible and make a copy of that documentation. With the internet, if it's there today, it could be gone tomorrow. Example is, when I was doing the Pac-Man emulation, there was this great document, 8 to 10 page document, on how to do a Pac-Man emulator, written by Chris Lamont. It was beautiful. I used it, got it working. I went back later to check it out, it was gone. He got a cease and desist letter from Namco. Apparently that stuff is a little too valuable to have around. So, don't rely on it being there tomorrow. If you see something great, take it and save a copy. You also want to do as much research up front as possible. You don't want to get halfway through the project and realize you're missing a critical component that prevents you from actually finishing your project. Also, evaluate the complexity. Some things will be easier than others. A 6502 is only 150 opcodes. It's not that bad. Now, a Z80 is more like 1,500. So it may not actually be more difficult to do the Z80, but with 1,500, it's a lot more you have to get correct. And doing the first 100 opcodes can be kind of fun, but getting towards the end can be quite tedious. Also requires a lot of patience. A lot of things are going to go wrong. It's going to be a lot of puzzle solving. You got to be up for doing that kind of stuff and enjoy doing this puzzle solving. You got to realize that failure is an option. It's really about the journey of writing the emulator, not about getting to the final destination. And that also, smaller projects are fun too. So, I do have my code that I've written for this up on GitHub, located here. This is an email address you can contact me at if you got questions after this. But in the meantime, we got 15 minutes for Q&A. Does anybody here have a question? Now, I may not have all the answers, but I can do the best. Yes?
Do you have any sense at the moment, because I know because you're writing it in this other language.
Yes.
Swift or Go, I forget.
Go, yeah.
I'm sorry. What is the relationship between the execution of your emulator versus what C64s were like in their, in their own sense? I mean, I would expect you don't have to be cycle accurate. You just need to be instruction capable. So what's it like?
Okay, so cycle accuracy is a lot of work.
Oh no, I didn't.
Yeah. Well, yeah, I know. So I'll tell you how I handled it. So for this, at first you don't worry about that. So you let the CPU run at full speed. Okay, especially when you're running tests. You want to run tests as fast as you can, so you run at full speed. Actually, when you actually start running the real emulator, you don't want it to run full speed because it's going to drain your battery pretty quick. So now when you actually have to do the video display and stuff like that happens every 60 seconds. So your run loop at that point is draw the display, handle your interrupts, and then run the CPU a bunch of times. Okay? I was actually lazy. I didn't even do the calculations correct. I was just kind of like 20,000. So I did like 20,000 instructions per loop. And it worked. It's not necessarily accurate, but it's close enough. So, and of course, you can make it go really fast if you want to. That's part of the fun too. So, got any other questions here?
Oh, just a comment.
Sure.
You mentioned archive or Internet Archive.
Yes, it is a great resource.
All of the Commodore materials are curated at bombjack.org.
Okay.
And they've got all of the books, all of the magazines, and they're collected specifically around this topic. Like when you were trying to understand what was happening in the ROM where you were disappearing into nowhere, I thought about Dan Heeb's toolkit kernel, which basically does a byte-by-byte description of what the kernel ROM looks like. So if you're trying to debug where you're stuck in it, you can read into it, and it gives you a narrative description, not just an assembly breakdown.
That's another thing to point out is that it's actually really fun to do this now because there's been so much work done before. There's a lot of documentation. There's a lot out there right now. You know, your chances of getting stuck is actually not that bad because there's so much documentation you can find. And if not, you can ask on the forum somewhere, and somebody can help you out. And basically, the method of last resort is to go read the main source code. So you can do that as well. Or vice source code, sorry. So I do got one more story, if you're all interested.
Yeah, go ahead.
So when I was doing the Pac-Man emulator, I was having a problem where a certain part of the screen wasn't displaying. I didn't know why. Okay? And I was pretty confused by that. Now, the Pac-Man machine doesn't need a full 64K of memory. It really only goes up to like 5,000 or something like that. But when I was running my emulator through, I saw that there was a lot of things being written to high memory for some reason, up in the C-thousands. Like, well, that doesn't make sense. Why be writing up there? There's nothing up there, okay? But I couldn't figure out why these two things on the display weren't working. And this is actually in a track mode. So what was missing was the high score and then the credit display. That's kind of like two odd things to be missing, right? I was perplexed for the longest time, and then actually went and read the main source code. And what actually happened was on actual Pac-Man arcade cabinets on the Z80 chip, they didn't hook up the A15 line on the address bus. So the A15 was completely disconnected. So what was happening is that when they're actually trying to access high memory, with that not being hooked up, it was actually properly going right into video memory. And I suspect it was actually a copyright protection mechanism. So if you actually try to put Pac-Man ROM in an actual working Z80, then it wouldn't look right. And I suspect it was just because if you're an operator and you're going to put this in location and try to make money, people don't want to play if they can't see how many credits you don't have. And if you don't have a high score, well, then what are you going to be shooting for? So those are some of the issues that you run into. So, any other questions? Yes?
Run into an instance where there was a hardware bug that you wanted to implement, and because obviously you're not doing cycle accuracy, so you'd have to do that in a different way.
No, never got to that kind of specifics in there. What was interesting is Pac-Man is notorious for a bug. If you get above like level 255 or something, that completely freaks out. So it's kind of fun to actually do the emulator, put it up, get to level 255, and see it freak out. I was like, well, then I must have done it right, because it actually freaks out in the same way. One thing to note on, when I gave this presentation at MagFest, I gave a less technical one. That was actually more about telling stories than actually doing technical stuff. I was asking if anybody there had brought a Pac-Man machine with them. Out of all places, I think MagFest would have been it, but nobody had one. Apparently, there's actually a switch inside the cabinet that when you press it, actually just advances to the next level. I don't know why that exists, but apparently it does. So apparently, I think you hit it like 255 times and you get to the kill screen. So, yes?
I noticed that you skipped sound emulation.
Yes.
An important part of an emulator would be sound.
Oh, it is. It
emulation,
is.
right?
But like sound's like a whole topic just in itself. So, you could actually do sound just by itself, right? You could actually just write your own SID chip player and all that kind of stuff without the sound. For the Commodore, I didn't do sound. For Pac-Man, I did, because I wanted to get something working. And it's probably about 96% correct. It sounds like Pac-Man, but it's just a little bit off. Yes?
Kind of a similar question. Did you implement any type of way of loading like cassettes or cartridges or code from the outside that you're not putting in?
Okay, so disk, when you're talking about disk, a disk drive is basically a full machine in itself back then. Actually, it had a 6502 in it too. That's just way too complicated. You could do tapes like that. I decided to take the easy route out, and what I would basically do, in my monitor, I would actually directly load files from my disk and just stuff it straight into memory. Yep. Mm-hmm. But I would actually have like a load command in the monitor to do it. So one thing to note about that, if you're loading in something that's like a basic program, there's actually 2 pointers that you're concerned about. One that's the start of arrays for your basic program, and one that's the start of variables. They actually initially point to the end of where the program is. So if you load in something directly like that, doesn't know about it, you actually have to adjust the pointers to be right after that. If not, when you start running the program, we'll actually start overwriting the program. So I just did it that way. I got enough up and running. I could play some basic stuff like that. I was actually going to give a quick demo today, but that's not going to happen. So. Anything else? Okay, well, I'd like to thank everybody for coming out today. Hope you enjoyed the talk.